one session here.
We're off.
Okay. Hello. Hi. I'm David Jacobs from Case Western Reserve University. Hans Darkman is my advisor. My poster title is Dark Fields and Modified Gravity Theories. Don't throw anything at me. The theory I'm looking at is generalized Einstein ether theory, which is essentially general relativity plus an additional fixed norm vector field, and that fixed norm quality makes it Lorentz violating. It also has a free function that describes its kinetic structure, so when I refer to modified gravity theories, I'm really referring to the set of different functions you can choose in this theory. So some of the things you can do with this, if you choose the correct function, you can, in a certain limit, obtain Mond, which allows you to reproduce galactic rotation curves. Using a different choice, you can achieve late-time acceleration and seed large-scale structure growth through the growing modes of this additional degree of freedom. Another analysis has been done doing weak lensing that can show that the lensing centers can be displaced from the luminous mass centers. And what I'm curious about lately is the time-dependent behavior, and thank you.
Alrighty. I'm Eric Suhida from right here at The Ohio State University. And if you know what IceCube, what I've been working with is a radio version of IceCube, where we pull some signals and look at the signals. And then what we want to do is look at the radio attenuation length in that Antarctic ice. So basically what we have is this setup here, a pulsar pulses. It's a dipole pulsar, and then there's a bunch of dipole antennas here to receive that emission. And what we do is basically look at the power absorbed, and we can know geometrically what we expect to absorb. It sounds really easy, I'm sure, but there's a lot of difficulties, so if you want to know what those difficulties are, go ahead and see my poster.
My name is Amanda Yoho, and I'm from Case Western Reserve University, working with Francesca Ferrara and Glenn Starkman. So we take WMAP temperature maps and mask them with some combination of the regions shown here, with the galaxy always masked out, and produce power spectra from those masked maps. So right here is our result from just using the first year release of the WMAP data. And you notice around the peak region, which is about at the degree scale, you see two lines which have decreased in power by about 10%. And those are created when you include the region from this north ecliptic cap. The ones that follow the general trend that we all know and love mask out the north ecliptic cap. So we take that to say that there's something going on in the northern region that's decreasing power. And we do have motivations other than just looking around in the data, so see my poster for that.
I'm Jim Davis. I'm here at CCAPP with Karsten Rutt. So for a given hit pattern in IceCube, we can do a likelihood analysis to find the single track that best fits that hit pattern. If we're now interested in identifying starting tracks, which we are, because a starting track that begins actually within the detector will indicate a neutrino, then we can assume a reconstructed vertex and see if this new track that begins within the detector better fits the data. The take-home message is simple. Rather than just using the single reconstructed track and the assumed vertex, if we take a single parameter to estimate the error that our reconstruction has, then we might be able to improve the ability to identify starting tracks, and this is especially important for deep core, where we might want to look at southern sky sources.
I'm Takayuki Tanaka from Nagoya University. So my poster title is WIMP Indirect Search from Sun and Galactic Center using Super Kami detector. So Super Kami is a water triangle of neutron telescope located Kamioka in Japan. So we performed indirect search and published our result in 2004. And this time we update our result. And we couldn't find any event excess comparing atmospheric background, but we make a good WIMP upcoming flux limit, especially low mass WIMP, and also get a good limit for the low mass WIMP in terms of spin dependent cross section. And also for the galactic center, we calculate the active flux limit and compare it to annihilation. Thank you.
Hi, I'm Rebecca Riesman. I'm a first-year graduate student here. I worked with Chinese Seagull Gaskins amongst with some people out in California. I currently just have a picture of this map because I thought we were using our posters. Anyways, I looked at millisecond pulsars as contributors to the high latitude gamma ray diffuse background, and to see how this could contaminate looking for dark matter. And we find that even in a maximal scenario that it shouldn't be too bad, because we don't expect dark matter to be sub 10 GeV. So that's good.
Okay, so I'm Michael Sutherland. I'm working here at Ohio State with Brian Boffman and Jim Beatty. And we don't know much about the galactic magnetic field, so we're proposing a method for constraining the parameter space for galactic magnetic field models. So you assume a composition, a source distribution, and a magnetic field model, and then you grid the parameter space for the magnetic field model and backtrack the events. And you compare the correlation number with the source catalog to the observed correlation number. And that lets you determine what scan points in your galactic magnetic field model parameter space are compatible with the assumptions you made about the source, the composition, and the magnetic field model. And then the two plots on the bottom show a particular scan where I made up a universe. I made a galaxy with a magnetic field model, backtracked some mock events, and on the left I scanned the actual magnetic field model, and then on the right I scanned a test model that's incorrect. And you can see that it seems to constrain that parameter space for the truth field model fairly well.
One more.
Hi, I'm Andrea Albert. I don't have a slide, but I hope you'll give me a minute of your time. I'm a first-year grad student here, and I worked this summer with Aaron Sander on a search for dark matter in the galactic halo. You can check out our poster out there. Essentially what it does is it shows the general idea of behind the dark matter search. It shows some of the different decay channels, the differential yield energy spectrum of those. It also describes our method, which essentially we take our dark matter signal. We also take our diffuse models, which we've used Galprop to make, and then we also take our instrument response functions, shove them into Guardian, and out comes a simulated counts map, which is heel pick spinned, and then we take that and we rebin it into 6 annuli, which you can see on our poster. And from that, what we've been doing is we've been running pseudo experiments in order to test our fit. And so what we do is we take our signal truth, and then we fit it with different fitting data that makes different assumptions about WIMP mass or density profile, and we see how those assumptions bias our fit. And also our fit is our pseudo experiments you can see in our posters show just how well actually our fitting is working, especially with the Via Lactea 2 profile. Thank you.
Very good.